Finding the perimeter of a rectangle is simple arithmetic. You plug the lengths into a formula, and you have your answer. But the real world rarely aligns perfectly into right angles and straight lines. When boundaries curve and become irregular, that formulaic approach breaks down. Students who can easily calculate the sides of a square on paper often struggle to estimate the distance around an odd shape, revealing a gap in their spatial intuition. The game Estimate and Measure directly addresses this. It replaces rigid calculations with physical experimentation. To play, you need a few basic tools: this printed game board, a piece of string, a 12-sided die, a pencil, and a standard centimeter ruler. The objective is straightforward. 2 players compete to be the first to successfully estimate and measure their way completely around their assigned track. By taking the ruler away during the initial guessing phase, players are forced to physically judge distance with their eyes and hands, which builds genuine measurement sense. Step 1 begins with a roll of the 12-sided die. The number that comes up is your target distance in centimeters for that turn. Here is where the mental work happens. The player looks at that number, say an 8, and has to visualize what 8 centimeters looks like as it bends along the curve of their irregular track. Once they have their guess, they use a pencil to mark that specific spot right on the perimeter line. To verify their guess, the player picks up the piece of string. Warning tone: it is tempting to simply loosely drape the string over the shape. However, doing that creates slack, which guarantees an inaccurate measurement. Instead, the player must pin the end of the string exactly at their starting point, then carefully press it flush against the curve, following the track all the way to their pencil mark. Keeping their finger firmly pinched on the string exactly at the location of their pencil mark, they carefully lift it off the board. They then pull that length of string completely straight and align it against the 0 mark on their centimeter ruler. This physical action, taking a bent, unpredictable curve and pulling it into a straight, standard unit of measure, is exactly how we demystify the concept of perimeter for these irregular shapes. We apply the margin of error, a tolerance of exactly 2 centimeters. If the string lands inside that window, the estimate is successful. If it falls outside, the estimate fails and the player loses their turn. Let's apply this to a real turn. A player rolls an 8, marks their guess on the track, measures with the string, checks it against the ruler, and finds it is 7.5 centimeters. Because 7.5 is well within 2 centimeters of their target of 8, it is a valid turn. They now lock in that pencil mark as their new starting position. Player 2 takes their turn, rolling, guessing, and checking. Then the board comes back to player 1 to continue from their new position. Over several turns, this loop creates a breadcrumb trail of pencil marks, moving steadily around the boundary of the track. Getting immediate feedback on every single roll trains the eye. If a student consistently overestimates, the constant physical checking quickly forces them to tighten their spatial predictions. To adapt the difficulty for younger students, you can simply widen that margin of error. Expanding the tolerance from 2 centimeters up to 4 centimeters keeps the game moving while they learn the basics of estimation. For an advanced challenge, give students a blank piece of paper and have them take turns designing their own erratic, complicated perimeters for an opponent to navigate. This introduces a clever psychological trick. In their effort to draw a boundary that will frustrate their opponent, the creator is actively engaging in deep geometric thinking about distance and curves. Through this interaction, you get conversations about strategy, scaling, and accuracy, discussions that rarely happen over the quiet repetition of a traditional math worksheet. True understanding of measurement relies on an intuition for physical space. By actively estimating, testing with a piece of string, and adjusting their guesses, students build a foundation that equations alone cannot provide.